Okay, so today we're going to extend this concept of connectivity that we've discussed last week. Okay, so last week when we discussed the proof for the sufficient condition of Hamiltonian cycle, we introduced this concept, the connectivity of a graph. Okay, so the connectivity is basically the minimum size of a vertex set that you need to remove in order to disconnect the graph, or to let the graph only contain one vertex. Okay, so today we're going to discuss more properties about connectivity. Okay, so we're going to start with what we call cut vertex and bridge. Okay. So what is a cut vertex? Okay, so let me first give you an example. Okay, so this is a kinetic graph, and what is a cut vertex? So a cut vertex is a vertex, okay, so it is not a vertex set, it is just one vertex. So the special property about this vertex is that if you remove this vertex, then the graph becomes disconnected, okay? So for example, in this 5 vertex graph, there's only one cut vertex, that is the one in the middle, okay? So this guy. This is a cut vertex. Okay. So the reason is that if you remove this vertex, and also after you remove a vertex, we also remove its instant edges. Okay, so all these 4 edges that are like instant to this vertex, they are also removed. Okay. So if we remove these 4 edges and this cut vertex, then the graph becomes disconnected. Okay. So this is a cut vertex. So when we discuss cut vertex, we always assume that the graph is connected, because if the graph is not connected, well, you don't need to remove any vertex to disconnect the graph. So yeah, we always consider a connected graph. Okay. So the definition is quite natural. So just remove the vertex and remove its instant edges. So if the graph becomes disconnected, then this vertex is a cut vertex. Okay. So the other 4 vertices, they are not cut vertices, because after you remove this vertex and there are 2 instant edges, the graph is still connected. So it is not a cut vertex. Okay, so a bridge. Well, the concept of a bridge is very similar to a cut vertex, but visually, a bridge is just like an edge instead of a single vertex. So the concept is still to remove one element, but this time an edge. Okay, so if you remove an edge and the graph becomes disconnected, then the edge that you just removed is called a bridge. And also when we remove an edge, okay, we only remove this edge itself. We do not remove its endpoints, okay? So this is a bridge. And so after you remove this bridge, the graph is disconnected, okay? But it still has 6 vertices. So you do not remove any vertices, okay? Just one edge. And once again, we only consider connected graph, okay? Because if the graph is already disconnected, then you don't need to remove anything. So an edge of a connected graph is called a bridge. If removing this edge disconnects the graph. Okay. So 2 very similar concepts, okay? So the basic idea is to disconnect the graph by just removing one element. But still, I want to stress that when we discuss cut vertex, we remove a vertex along with its incident edges, okay? So it's like it's more powerful to remove a vertex because when you remove a vertex, all its incident edges are gone, okay? Okay, so today we're going to first discuss some relationships between cut vertex and bridge. So I have 2 questions for you. So the first one, so say you have a bridge, UV, okay? Okay, so you have a bridge with endpoints U and V. So can you always say that these 2 endpoints are cut vertex? Okay. Yeah. So for example, in this case, we have this bridge, okay, with endpoints U and V. And indeed, in this example, if you remove U and its incident edges, then the graph is disconnected, okay? So similarly, if you remove V, then the graph is disconnected, okay? So in this case, the answer is yes, okay? So both endpoints are cut vertex, okay? So is it true for any graph and any bridge? So that's my first question. Second question is, this time we start with a cut vertex. So if V is a cut vertex, then some edge incident to V must be a bridge. Yes or no? I think for the second question, it's easy to see that the answer is no, because I just gave you a counterexample, okay? So this is a cut vertex, okay? But neither of these 4 edges is a bridge, because no matter which edge you remove, the graph is still connected, So the answer is no. Now how about the first one? Actually, the answer is still no. So can you give me a counterexample? This is like a corner case, okay, a very special case where one of its endpoints may not be a cut vertex. Yeah, so this is one case where you just have two vertices and one edge. So by definition, this is a breach, okay, but these two endpoints, they are not endpoints. They are not cut vertex, okay? So another possible case is like this. Okay? So in this graph, this is a breach. Okay? But this time, U is not a cut vertex, okay? Because after you remove U from the graph is still connected, okay? So the answer is no, okay? Okay, but if I add more constraints to this breach, or on these two endpoints, then the answer will be yes, okay? So the constraint that I'm going to add is that the degree of U is at least 2, okay? So if the degree of U is at least 2, this means U has one more neighbor, okay? So in this case, you can see that if I add one more neighbor to U, then removing U will disconnect U's neighbor from the remaining part of the graph, okay? So if the degree of U is at least 2, then U is a cut vertex. So similarly, if the degree of V is at least 2, then V is a cut vertex. Okay. Okay, so next, let's consider a very simple property about breach. Okay. Okay, so this time we're going to consider cycles and breach. Okay. So the claim is, once again, let's consider kinetic graph. Okay. So this gives a necessary and sufficient condition for breach. Okay. So it says if one edge is a breach, then you cannot find a cycle that contains this edge, okay, or passes through this edge. Okay. Well, this time the claim is correct. Okay. So we're going to prove this. Okay. So there are two directions. So first of all, we're going to consider the so we have an edge, we know that it is a breach, and want to show that there's no cycle that can contain this breach, okay? So this is the first direction. And the second direction, we're going to start with this assumption that no cycle, so you cannot find a cycle that uses this edge, then we can show that this edge is actually a bridge. Okay, okay, so let's first consider the first condition or direction. Okay, so you have a bridge at hand, and you want to show that you cannot find a cycle that contains this bridge. Okay, so you have a bridge that's called U and V, and the reason that this is a bridge must be the case that if you remove this edge, then you get two components. Okay. So let's call these two components A and B. Okay. So this is why this is a bridge, and there's no other edge between A and B. Okay, because if there's one more edge between A and B, then this guy cannot be a bridge. Okay. So if you have an edge like this, then after you remove U and V, A and B, they are still connected. Okay, so you cannot have an edge between A and B other than this UVH. Okay. So this is like the graph. Okay. So we have two components and one edge UV between these two components. That's the whole graph. So I think it's easy to see that we cannot have a cycle that passes through this edge, because if there's a cycle that contains this edge, then certainly we're going to see another edge between the two components A and B. Okay? So this direction is quite simple, okay? So just use the definition that if this is a bridge, then removing it will create two components, okay? So about the other direction, so if you have H and you cannot find a cycle that contains this H, then this H must be a bridge. In other words, if you cannot find a cycle, then removing it disconnects the graph. Okay. Okay, so I think it's easier to prove it by contrapositive. Okay, that is, so this is P. And this is Q, okay? So the statement that we're going to prove is equivalent to if not Q, then not P. Okay? So we're going to show that if UV is not a bridge, then there's a cycle that passes through it. Okay. So I think this is quite easy. So perhaps you can figure out the proof. So this time you need to create a cycle, okay? So you have an edge, which is not a bridge, and you need to create a cycle or find a cycle that contains this edge. So how to do this? So this is not a bridge. And we need to create a cycle that contains this UV edge. Okay. Or in other words, we need to create a path between U and V. Because if we can create a path between U and V, then adding this edge will create a cycle. Okay. So how to create a path? Or how to show that there must be a path connecting U and V. 上一张投影片。一定有一个Yeah, similar idea. So if this is not a bridge, then removing it cannot disconnect the graph. So the graph is still connected, even if you remove this edge. Okay, so let's remove it. And since the graph is connected by definition, if it's a connected graph, then for any two vertices in the graph, you can find a path. That's the definition of a connected graph. Okay, 所以只要是 connected graph 的意思就是它的定义就是任两个点它都可以有一个 path。OK， 所以我们把 UV 删掉之后，这个 graph 我们刚刚说的是 connected， 因为它不是一个 bridge。也就是我们刚刚的假设，就 bridge 就是会把图变成 disconnected。那既然它不是 bridge， 那就代表你把它删掉，一样不会是disconnected， 所以它一样会是 connected， 所以就一定会有一个 path 连起来。OK， 所以有一个 path 连起来，这样你就会有一个 cycle。OK， Okay, so I'll use this notation G minus UV. This means I remove UV, this HUV from the graph. Okay, so we know that this graph is connected. Okay, because UV is not a bridge. So after removing this edge, you still get a connected graph. Okay, so since this is a connected graph, so there must be a path between any two vertices, including U and V. So you have this path. Along with this edge, you get a cycle. Okay. Okay, so I think with that, we've concluded our discussion on bridge and cycle. Okay, so if we use the notation kappa G that we introduced last week, so if a graph has a cut vertex, then the connectivity is 1, okay? So let's recall the definition of connectivity, okay? So this is the minimum size of a vertex set, okay? So when we consider connectivity, it may be the case that we need to remove multiple vertices in order to disconnect the graph. But for the case where we can find a cut vertex, well, we can just disconnect the graph by removing one vertex. So it must be the smallest possible, okay, for a connected graph. So if a connected graph has a cut vertex, and we know that the connectivity must be 1, okay? Okay, so how about bridge, okay? Because last week when we discussed how to disconnect a graph, we only remove a vertex, okay? But this time we're going to consider the case where we can just remove edges, okay? And the definition will be very similar, okay? So I can just copy paste this definition. But this time we're going to call this edge connectivity. And the notation will be kappa prime, okay? So whenever you see prime, it may be the case that it is related to edge, okay? Okay? So the only difference is that this time we remove an edge set instead of a vertex set, okay? Okay. Okay, so when we discuss edge connectivity, and if we have a bridge, then we know that the edge connectivity is 1, okay? Because you can just remove the bridge to disconnect the graph. Okay. So when kappa G or kappa prime G is 1, this is like the weakest kinetic graph, okay? Because you can just destroy the graph. By destroy, I mean disconnect, okay? You can destroy the graph by removing just one element, like one vertex or one edge, okay? So next, we're going to consider like stronger graphs, where you need to remove multiple vertices or multiple edges. Okay, but before that, I need to define a few terms. Okay. So next, I'm going to define this separating set. Okay. So separating set is a set of, it can be a set of vertices or a set of edges. But the concept is that once you remove this separating set from a graph, then the graph is disconnected, okay? So this separating set is just like this edge set, or the vertex set when we discuss vertex connectivity, okay? So, but this time we have two types of sets, okay, edge set or vertex set. So I'm going to differentiate these two sets by saying separating vertex set and separating edge set. Okay, so yeah, the definition is very similar to the set we've seen in the definition of connectivity. Okay, so this is separating vertex set. So we also have separating edge set. Okay, so after introducing these two sets, we can also like redefine connectivity. So what is connectivity? Well, connectivity is like the smallest separating set. So when you consider vertex connectivity, it is the smallest separating vertex set, okay? Or when we discuss edge connectivity, this is the smallest size of separating edge set. Okay, and another term that you may see in your graph theory paper is that is these two terms, okay? K connected and K edge connected. So we say that a graph is K connected. If the connectivity is at least K, okay, that's it. Or if we consider edge connectivity, then if a graph is K connected, it means the edge connectivity is at least K, okay? So for example, if you see a graph that is 1 connected, well, this means the graph is connected, okay? Okay, and if you see a 2 connected graph, this means the connectivity is at least 2. So when the connectivity is at least 2, so this means if you want to remove or disconnect the graph, okay, you have to remove at least 2 vertices. In other words, if you only remove 1 vertex, the graph is still connected. Okay, and this vertex can be any vertex, so no matter which vertex you remove, the graph will still be connected, okay, if it is 2 connected. So similarly, if there's a 5 connected graph, well, this implies the connectivity is at least 5. So this means if you want to disconnect the graph, you have to remove at least 5 vertices, okay? In other words, if you only remove 4 vertices, then the graph is still connected, okay? Okay. So in general, if the graph is k connected, this means no matter which k minus 1 vertices that you remove, the graph will still be connected. Okay. So I want to stress that this is any k minus 1 vertices. Okay. So likewise, when we consider kh connected, this means the graph is still connected after removing any k minus 1 edges. Okay. 你说这个吗？嘿，你的问题是，你说如果是 one connected 的意思是什么吗 ？OK。Let's just apply the definition up there. Okay, so one connected means kappa g is at least 1. So if kappa g is at least 1, this means the graph is connected, right? Because you need to remove at least 1 vertex. If you do not remove anything, the graph is connected, okay? Yeah, that's it. So it's connected. But when this connectivity is greater than 1, we can say more things, more properties about the graph. Like, so when kappa g is at least 2, you can actually remove 1 vertex, and any vertex actually, no matter which vertex you remove, the graph will still be connected. Okay, so let me give you an example. So for example, can you give me a graph that is 2 connected? Yeah, that like a cycle, okay? So this is 2 connected. So when I say that a graph is 2 connected, it can be the case that the connectivity is really high. It may be like 10 or 100, okay? So it only like poses a lower bound for the connectivity. So the lower bound is that the connectivity is at least 2. Okay, but in this case, well, since this is a cycle, so the connectivity is exactly 2, because you can disconnect the graph by removing not any 2 vertices. You need to remove 2 non-adjacent vertices. Okay. So, and this is the most efficient way if you want to disconnect the graph. Okay. You cannot disconnect the graph by removing just 1 vertex. Okay. So this statement says that if it is 2 connected, then the connectivity is as 2, and the graph is still connected after removing 1 vertex. And indeed, in this example, no matter which vertex you remove, the graph will be still connected. Okay? Okay, so today we're going to discuss more properties about two kinetic graphs. Okay, but before that, I want to discuss more general relationship between edge connectivity and vertex connectivity. OK， 所以到这边有问题吗？所以我们刚刚做的事情是稍微整理一下我们刚刚这节课做的事。第一个，我们就考虑connectivity 是一的状况，就是如果你有 cut vertex 或者你有 bridge， 这种状况就是你把那个 cut vertex 删掉，这个 graph 就会变 disconnected， 或者你把这个 bridge 删掉，它就会变 disconnected。所以在那个有 cut vertex 的情况下，我们就会说它的 connectivity 是一。OK， 然后在有 bridge 的情况下，就是它的 edge connectivity 就会是一。所以我们要考虑两种 connectivity。我们上礼拜谈的那个是算是 vertex 的 connectivity。那我们刚刚有看到另外一个新的 concept， 就是去看 edge 的部分。你要拿掉多少个 edge， 才可以让这个 graph 变成 disconnected。所以这有点像是去看这个网络或这个 graph 够不够强壮，够不够坚韧这样子。如果够坚韧、够强壮，那应该把你少掉几个点或少掉几个边，应该不会影响这个网络的它的 connected 与否。OK， 那我们因为时间差不多到了，我们就先休息一下。然后我先预告一下，我们今天还会去看就是 edge connectivity 跟 vertex connectivity 的关系，谁比较大，谁比较小。OK， 然后我们还会去看一下针对这种 two connected graph。去找一些它的有趣的性质 ，OK， 好，所以我们就先休息一下。 All right, so in the previous case, we mainly focus on one connected graph, okay, or graph where the connectivity is 1, okay? So next we're going to consider graphs where connectivity can be greater than 1, okay? So we're going to consider some relationship between kappa G and kappa prime G, okay? That is vertex connectivity and edge connectivity. Okay, so let's begin with two simple properties, okay? The first one compares kappa G and the minimum degree. Okay. So here we have two quantities. So the first one on the left is the connectivity. That is the smallest number of vertices that you need to remove in order to disconnect the graph. And on the right, we have the minimum degree. So minimum degree is just, well, the smallest number of neighbors that a vertex has in a graph. Okay. So which one is larger? Or it depends. Perhaps in some graph, kappa G is greater. Perhaps in different graphs, the minimum degree is larger. 大概所以哪一个会比较大，哪一个比较小？ kappa G 比较小，比较大。所以这个是你至少最少要删掉的点，才可以让它变成断掉 ，OK。然后这个是整张 graph 的最小的 degree。对，哪一个比较大，哪一个比较小？ 对，这应该没有很困难 ，OK。And the second question is similar, but this time we compare kappa prime G, that is the edge connectivity, and the minimum degree. Okay. OK， 所以听听大家的想法 ，OK。所以觉得 minimum degree 比较大 ，OK。有可能会一样吗 ？OK， 有可能会一样的。OK， 好，这位同学，对，就你，对。所以下面这个 minimum degree 比较大，还是 edge connectivity 比较大？ 不一定，所以我刚刚听到不一定。OK， 不 OK， 所以不一定 OK。OK， 有什么原因吗？或者什么直觉会告诉你觉得 minimum degree 比较大？ OK， 所以你知道 edge connectivity 是什么吗？就是这个 kappa prime G 是什么，你知道吗？ 没有，如果不知道没关系，我可以再讲一次。但我要先确定是不是，因为如果知道，但是不是很确定这个问题的答案。OK， 所以我在讲是因为某种程度这可能会是我最后上的这两个小时，因为接下来我们就要 paper 的报告。OK， 所以 Kappa G。那今天要讲的都跟我们之前的没有关系，所以某种程度你过去15周、10几周你都没有在听，你还是可以 follow 今天的课程 ，OK？ 所以 Kappa G 是你最少要删掉的点的个数，一旦你把那个点删掉，就包含你旁边的它的边也一起删掉，然后会让它图变成 disconnected，OK？ 所以这是 Kappa G， 所以你至少要删掉几个点，你在删掉的时候，你会把那个点它相邻的边也都删掉，这样才可以让整个 graph 变成 disconnected， 然后 Kappa Prime G 是你至少需要删掉几个边，才可以让这 graph 变成 disconnected。OK， 好，所以哪一个？你说什么？你说小于？不会等于。OK， 所以永远不可能找到一个 graph 会让它等于，是一定是这样子。你也同意他说的？OK， 好。Sorry， 你可以再说一次。OK。OK， 所以这位同学你觉得？OK， 那为什么有什么直觉吗 ？OK， 现在看起来我都已经写上去了，大家不会有人说是大于了 OK， 所以大家用猜的，就算你没有 follow， 你应该会猜小于，所以我要为什么 ？OK， 所以为什么是小于？我会说就是，答案其实很简单，所以如果你们没有 follow， 那代表我的定义讲的不够清楚，就只有这个可能性 ，OK。所以这没有想象中那么难，这个事实上是很简单的，很简单我才问大家。譬如说，随便举一个例子啊 ，OK。所以假设我今天要你解释说，给你一个图，然后我要你解释说，它的这个图的 connectivity 小于等于3，那要怎么证这样子的一个 statement？ 你要怎么去说服人家？当然，其中一个方法是，就真的把那个最小的那个删掉的方法找出来。那有没有其他更简单的方法去说明说，Kappa G 不会超过3？我不想要真的找到那个最小的那一个删除点的方法。所以，譬如说你要说明 Kappa G 小于等于3，你唯一会需要做的是 ，sorry， OK， 这个图有可能不是 complete graph， 就任何一个 graph， 任何一个 graph， 然后我想要说的是，当你要去说这样子的一个 statement 的时候，其实你不需要真的把 Kappa G 算出来。因为算 Kappa G， 你会需要找出哪一个删掉点的方法是最少，这可能很复杂，你不需要做那么复杂的事情 ，OK？ 你唯一会需要做的事情就是去找，就你只需要说，这个 graph 你可以找到3个点，然后这3个点移掉之后，它就会变成 disconnected。如果你可以说明这句话，那事实上它的 connectivity 就会小于等于3。 因为 connectivity 是最好的那个方法。OK， 有可能会删掉2个点就可以，有可能删掉1个，但我不管，就是我只要找到一个方法，它只要删掉3个点就可以让它变成 disconnected， 我就可以知道说它最好的那个方法一定不会超过3。OK， 所以这个算是整个背后的思考的直觉。OK， 所以换句话说，如果你要说明这样的 statement。你要说明的是，就是你可以删掉一些点，删掉 minimum degree 的点。OK， 假设 minimum degree 是7好了，那你就只要去说明说，你可以删掉7个点，然后让这个 graph 变成 disconnected。OK， 那下面这个也是一样，只是这个下面会变成删掉 minimum degree 的 edge。OK， 所以这个答案都会是小于等于 OK。那所以现在关键是要怎么解释说这个是小于等于？大家有 follow 我刚刚这边说的吗？所以这边说的事情是你要去说明 connectivity 不会太高 ，OK， 不会超过3，那你只需要找，比如说找3个点，你把它删掉，这个 graph 就会变成 disconnected。因为如果是有这样的3个点，那我就可以知道最少的3的方法一定不会超过3个。所以 connectivity 就一定会小于等于3 ，OK。然后这边的话就是只是把这个3变成一个 minimum degree， 所以我们要找出来是到底要删掉哪一些点，才可以让它变成 disconnected。G 的 minimum degree。Sorry， 刚刚没有写清楚 ，OK。所以我们看的都是某一个 graph，OK。假设我随便画一个 graph。OK， 所以像这个 graph 里面，它的 minimum degree 就会是2，因为像这个点它的 degree 就是2 ，OK， 那是最小的 degree。所以我就说这个 graph 不管我怎么画，我刚刚画的多复杂，它的 connectivity 就一定不会超过2。H connectivity 也是一样 ，OK， 所以这个例子里面 H connectivity 就一定不会超过2。所以现在问题是你要，因为你现在找到它的弱点，就是这个 graph 它的脆弱的点在哪里 ？OK。就这样子，没错。所以，比如说像这个点，它有最小的 degree， 那我要怎么说明上面这个？我只要首先我就把最小 degree 的点抓出来。如果要让这个图变成 disconnected， 那我就是把它的 neighbor 删掉。那这个点它就连不到外面的 ，OK。然后同样的这个 edge connectivity，edge connectivity 我们就要删边嘛 ，OK。所以这个时候我们就不会删 neighbor。我们就删它跟 neighbor 的边，把它删掉。那这样子这个 graph 就会断掉 ，OK。所以，OK， 所以我稍微写一下。Okay, so let's let V be the smallest degree vertex. Okay, so in this case, V has 4 neighbors. Okay. So all we have to do is to just remove every neighbor of V. Okay, and there's a corner case where this is the whole graph. That is, the whole graph just consists of V and its neighbors. So if you remove all neighbors of V, then the remaining vertex, the only remaining vertex will be V. But this is okay because when we discuss or when we define connectivity, okay, when we define connectivity, we have this corner case where the remaining graph only has one vertex. Okay. So if I remove all neighbors of V, then either the graph is disconnected or the graph has only one vertex. And that's it, okay? So the connectivity of the graph cannot be greater than, must be smaller than or equal to n of V. In other words, it is at most the size of mv. And this is just the degree of V, which is the minimum degree. Okay. OK， 所以我觉得整个最关键其实应该是要看出这个逻辑的转换，就是你要说明这个 connectivity 不会很大，不会超过某个数字。那你要做的事情就是找出那一个数字的那些点，然后把它删掉，然后说明这个 graph 会变成断掉。OK， 那这样子你就可以知道，哎，最少的那个点的个数一定不会超过刚刚那个。Okay, and the proof for edge connectivity is almost identical. Okay. So the only difference is that this time we remove the edges. Okay. Okay. So we do not remove MV, we remove the edges between V and MV. Okay. And since we do not remove any vertex, we don't have to consider a case where it only has one remaining vertex. Okay. Okay. 有问题吗？所以这就是一个暖身，这不是我主要想要讲的 ，OK？ Okay, so far we've considered or compared edge connectivity and minimum degree, or connectivity and minimum degree. So this time we're going to directly compare kappa G and kappa prime G. Okay. And the question is the same, okay? So which one is larger? Which one is smaller? So 这是就是有点像两个方法 ，OK？ 这第一个方法是移掉点跟边，这边的边就是相邻的边，然后一边是只移掉边 ，OK？ 那哪一个方法有点像它可以移的 element 的个数会比较少？是移那个 vertex 的方法可以移比较少，还是移 edge 的会比较少？嗯哼。那我们把 bridge 砍掉，不代表我们会删掉那两个 endpoint， 因为我把 bridge 删掉，我只有删掉那个边而已，我并没有把它两个 endpoint。对，近似于，但是对不完全相等。对。对，我们稍微想一下刚刚那两个方法。So when we consider kappa G, we remove vertices along with their instant edges. So by removing vertex, I also remove more edges, okay? But when we consider kappa G, we can only remove edges. All the vertices are still there, okay? So we do not decrease the number of vertices, okay? So which operation is more powerful? Sorry? Yeah, okay. So if this is a more powerful operation, we should be able to use less operations to disconnect the graph. Right? So using this intuition, kappa G should be at most kappa prime G because it is a more powerful operation. All right, so now, can you give me an example where, say, kappa G is only 1, but the edge connectivity is very high? Okay, so we have a star. Well, for star, both edge connectivity and connectivity are 1, okay? And let's recall the first example we considered today. Yeah, this one, okay? So since there's a cut vertex, so connectivity is 1, but there's no bridge, okay? So the edge connectivity is at least 2, okay? So in this one, well, at least this example shows that they can be the same, okay? Kappa G can be equal to kappa prime G. But in some graph, kappa G can be strictly less than kappa G prime. Kappa prime G, okay? That is, the connectivity can be strictly less than the edge connectivity. Okay. Okay, and I think it's easy to see that we can actually increase the edge connectivity here by introducing more edges. Okay. to increase kappa prime g, like this, okay? So it can be many edges. So it's like a butterfly, right? And all this is a complete graph. Okay, sometimes we call it a clique. Okay. So it's like you have two components, two complete graphs joined by a single vertex here. So if you remove this vertex in the middle, you disconnect the graph, so kappa g is 1. But if you can only remove edges, then you need to remove lots of edges, okay, to disconnect the graph. So edge connectivity can be really, really high, okay. Sorry. 你说这边吗? Well, not necessary. Yeah. Yeah. Okay, but these are just some intuitions. So we need some formal proof. Okay. So next we're going to show that this is indeed the case for every graph. Okay. Okay, so let me first give you the high-level idea behind the proof, okay? So I want to show that kappa g is at most something, okay? So this is the structure that we've seen here. Okay, so we want to prove that kappa g is at most something, okay? So all we have to do is to show that we can disconnect the graph by removing this something vertices, okay? So all we have to do is to show that we can disconnect the graph by removing kappa prime g vertices. Okay? So if we can do this, we finish the proof. Okay? So in other words, today we almost only consider like the upper bounds for connectivity. Okay? So one upper bound is the minimum degree. And the upper bound we have here is the edge connectivity, okay? All right, so by this time, how to find this kappa prime g vertices? So previously, when we only consider minimum degree, it's quite easy. Right? Just identify the vertex with the smallest degree and just remove all the neighbors, and that's it. So about this time. Okay, so recall that we've defined this term separating H set. This is an H set such that if you remove it, you disconnect the graph, okay? And let's use F to denote the smallest separating edge set. So we know that F is kappa prime g, right? Because kappa prime g is the smallest number of edges that you need to remove to disconnect the graph. So by definition, this is the size of the smallest separating edge set, okay? And because the graph is disconnected, if you remove f from the graph, so visually the graph looks like this, okay? So after you remove f from the graph, you get two components, okay? And f is precisely the edge set between A and B, okay? So if you want to disconnect the graph, then you have to remove all the edges between A and B, okay? All right, so now how to find our kappa prime G vertices, okay? So still want to remove to disconnect the graph by removing vertices, not edges, okay? 随便挑一个，这句话是什么？OK， 每一个边随便挑一个 ，OK。So the first suggestion is for every h, you So it's like we have a for loop that checks every edge in F, and for every edge, we just remove one of its endpoints. And there are no constraints about which endpoint should we choose. Okay, you can choose any one of them. Okay. So is this valid? Can we say that after you remove this endpoint, you get a disconnect graph? 所以我们现在就是有这个 F，OK，F 是一个边的集合，它就横跨两个 components A 和 B， 然后我们的目标是要去找这个 kappa prime G 这么多个 vertex， 然后这么多个 vertex 删掉之后，它就会变成 disconnected。所以刚刚有同学做的建议是就，那既然我们就是要删掉这么多，看有几个边，我们就要删掉几个点，那我们就每一个边都删掉一个点。那这样似乎看起来 A 跟 B 就会被分开了 ，OK？ 因为 A 这边如果有一些点 ，B 这边有一些点，你把这个桥梁，你把这个 endpoint 删掉，这个桥梁就全部都不见了，这两个点就没有办法连在一起 ，OK？ 就像这样子，所以这有一个 U， 这有一个 V， 所以你把刚刚这些边全部删掉之后 ，U 跟 V 就没有 path， 没有 path 就代表它们变 disconnected。但有一个 corner case。有一个状况是这个没有办法考虑到。有。OK。什么意思？啊哈。一个 component 一个点，然后它连过来，啊哈，这个是一个 bridge， 啊哈。那如果在考虑这条 bridge 的时候，我移掉这个，那它就没办法变成这个点，所以。OK， 你的意思是这样吗？它要加一些糖水，就你的 A B 两个 component B 这一个点。哦 ，OK， 现在就一条 bridge， 现在 bridge 就只有一条，所以如果你不行，随便一个点，那不行，因为如果你不是那个。OK， 所以你的意思是说，如果我移的就是 A 里面这个点， 移完之后，这个 B 一样会是 connected。没错，这就是事实上可以再稍微更 generalize 一点，就有可能 A 所有的点都是在上面的 endpoints， 所以不一定是说 A 就是只有一个点，就是有可能说 A 上面这个 A component 里面的 vertex， 它们都是在 F 里面的 endpoints。那这样子，你把这些 endpoints 全部删掉之后 ，A 就没东西了。OK。OK。OK， 所以我们会需要稍微修正一下我们的方法。OK。不过我觉得要讲这个 proof 的原因，主要是我想要跟大家讲这个corner case。OK， 就是刚刚这个很直觉的做法，事实上是有问题。那至于怎么解决这个问题，我觉得坦白讲，我倒觉得没有那么重要。OK。Okay, so we're going to divide the proof into two cases. So the first case is when every vertex in A is adjacent to every vertex in B. Okay? So visually, this is like, well, this is like a complete bipolar graph. Okay. If you only consider edges in F. Okay. Yeah. So basically, for any two vertices, okay, one in A and the other in B, they are adjacent. Okay. Okay. So this is the first case. Okay. And this is kind of the reason that the previous proof fails, because if you can see that if you remove all the endpoints, then A will be empty. Okay. Okay. But for this case, it is quite trivial. The reason is that, well, this time the size of F is quite large. And recall that kappa prime G is just the size of F. And in this case, the size of F is at its m minus 1. Okay? So because the sum, okay, the sum is n. Okay, so this is the whole graph. All right, so the number of vertices is n, so you can divide n into two numbers and consider the sum, or perhaps I should write this is the product of the size of A and the size of B. Okay, and their sum, the size of A plus the size of B is n. Okay, so this is at its m minus 1. Okay, so this happens when A only has one vertex and B has all the remaining vertices, or vice versa. Okay, so for any other cases, well, you can only have more edges. And so if kappa prime G is at its m minus 1, then this is certainly greater than or equal to kappa G, okay? Because you only need to remove m minus 1 vertices to disconnect the graph or to make the graph only contain one vertex, okay? So this case is trivial, okay? So recall that all we wanted to show is that edge connectivity is greater than or equal to vertex connectivity, okay? So in case one, the edge connectivity is extremely high. It's so high that it is greater than the number of vertices. Okay. So this is like the trivial case, but this is the reason that the previous proof fails. All right, so this is case 1 and case 2. Okay, so let me give you a picture showing case 2. Case 2 happens when not every vertices in A and B are adjacent. In other words, you can find some vertex A, some vertex in A and some vertex in B such that they are not adjacent. Okay? So this is like the remaining case, right? Because in this case, we assume that every possible pair of vertices between A and B, well, they are adjacent. So if this case does not hold, then it must be the case that you can find some vertex in A and some vertex in B, and they are not adjacent. Okay? And still, our goal is to find for every edge in F, I want to find one endpoint. But this time we have to pick this endpoint with care. For each edge in F, okay? So there's still a for loop. We have to check every edge and pick one endpoint. And this time we want to to separate U and B. We want to make sure that there's no path between U and B, okay? After we removing all these endpoints, okay? Let me first explain this first case, okay? Okay. So the first type of edges in F that we're going to consider is like edges between U and, but that's it. The one endpoint is U, okay? This is the first type of edges that we're going to consider. Okay, so for this type of edges, we just remove, remove U. No, remove, remove V prime, okay? So what is v prime? V prime is just the other endpoint. Okay. So one endpoint is u, and the other endpoint that's called v prime. Okay. So we just remove v prime. OK， 所以我们的最基本的想法还是一样，跟前面是一样，就是每一个 f， 所以等一下我会画更多介于 a 跟 b 的 edge， 这些都是 f 里面的边 ，OK， 所以每一个在介于 a 跟 b 的边，我们都会挑一个 endpoint，OK， 我们之前第一个方法没有特别讲要怎么挑这个 endpoint， 这边我们会特别讲，这边我们挑了就是 u 的另外一个 endpoint。OK， 所以不要忘记，我们这个 case 2就是有特别先选了特别的两个点 u 跟 v， 这两个 u 跟 v 是没有相邻的。那也因为没有相邻，所以这里的 v prime 就不会是 v。OK， 因为我们一开始假设 u 跟 v 是没有相邻。那在这种 edge 里面，就是跟 u 有相邻的边，我们就会删掉 u 的另外一边的那些 endpoint， 所以就是这些 v prime。OK， 那另外一个就是。E 是没有跟 U 有相邻的。Okay. For this type of edges, we remove U prime. Okay. So these highlighted vertices are the vertices that we remove to disconnect the graph. Okay. Okay, so there are two things that I need to explain. First is the graph disconnected after we remove these vertices? So that's the first point. And the second point is that we need to make sure that A and B are not empty, okay? Because if A and B are empty or one of them is empty, then just like the first proof, it fails, okay? Okay, so first, why is this disconnected? This is disconnected because U has no path to reach V. What, for U to have a path to reach V, well, the first option is to use these bridges or these edges between U and this V prime. But this time we have removed all this V prime, okay? So we cannot use these edges. And the second option is to use this type of edges, okay? But since we also remove these edges, so you cannot use these edges to reach V, okay? So U and V are disconnected, okay? And since U and V are still in the graph because we do not remove U, okay? And we do not remove V. The reason that we do not remove V is that this V prime, they cannot be V, right? Because if V prime is V, then this means U and V are adjacent, okay? 所以这边稍微有一点点复杂，就是我们要解释的是，要解释两件事情 ，OK？ 第一件事就是我们删掉了这些点，真的可以让 graph 变成 disconnected。那我们这边做的事情是确保 U 它没办法走到 V， 那 U 如果想要走到 V， 它第一个就可以直接用 U 连过去的边，那这些边都已经不会存在了，因为我们都把它们对面的点、对面的这个 endpoint 删掉 ，OK， 所以这些边都没有办法用。所以它如果要横跨到 B 的话，它就要用剩下的这些 H， 可是剩下的这些 H， 它们在 A 这边的端点也都被删掉 ，OK， 所以这个它就不会是 disconnected。那为什么 A 跟 B 都不会是空的？因为 U 跟 V 都还会在 ，U 跟 V 都不会被删掉。U 没有被删掉的原因是因为我们在考虑第一个 case 的时候，U 是被保留的，我们是删对面。然后我们在考虑第二类的时候，第二类没错，我们是删 A 的点，但是第二类都是没有用到 U 的，所以我删掉这些点不会是 U。OK， 那另外一个就是这边 V 没有被删掉，原因是因为在第一类的这些 V prime 它不会是 V， 因为这边有讲了，就是因为 U 跟 V 是不会相邻的 ，OK， 所以你删掉这个 V prime， 这个 V prime 一定不会跟这个 U 跟 V 不会连起来。OK， 所以这个 V prime 就一定不会是 V， 所以在这个第一步 V 不会被删掉，然后在第二步这个 V 也不会删掉，因为第二步我们删的是 A 这边的 endpoints。OK， 所以这就是 proof， 所以有点复杂。OK， 我觉得重点就是这个 proof 是有问题的。我觉得某种程度这个比较重要 ，OK， 就是你不能随便乱删，随便乱删会有一些问题 ，OK， 好，所以我们就先休息 ，OK。我就打错嘛，哦，对，这个是 V， 谢谢。哦，是。
就那问起来感觉很白痴，就是
不会，
应该不会，就这是反正就是可以随机的嘛，就不用指定说谁要是 A B 是 B 哪个 set， 这样对不对？就反正任意两个 set 就可以。
任意两个 set 都可以，这句话的意思，你说这个 A 跟 B，
对，就不用指定嘛，人就随便，就不用指定。我决定哪一个是 A，
对，
哪一个是 B。
如果不用指定，那就代表说，譬如说全部都 A 也 OK。
不是，我重新讲一下我的问题。我只是想问说，就是因为你这边是指定的 A 跟 B 两个 set。
对，但是我之所以会有 maybe 我要先解释一下 A 跟 B 怎么得到的。A 跟 B 是这样得到，就是你把 F 删掉之后，就会有两个 components 跑出来，然后 F 就会是那个最小的 separating edge set。
所以还是要先做这件事，才有后面这边。
刚刚的逻辑是这样子，对，所以我那个
应该要这样串起来，然后应该就是这个做这件事之后，才考虑就是删点的这个情况是怎么删的，是这样吗？
我觉得我没有完全理解你的问题。
因为你不是说这里，你是说先用这个 F， 然后把它删掉之后，才有 A 跟 B 两个
component 嘛？对，没错。
对，那我是想问的是，这两个是有，就是你一开始就要决定好，就是这两个哪一个，这一个图中是哪两个 component 吗？还是随便都可以？就随便选哪？还是就是一定要经过找这个
？OK， 了解。因为我们的目标是要去说这件事情。对，所以为了要说明这件事，就是 connectivity 最多就是 H connectivity，然后就是跟前面的那个这边的 proof 一样，就是我们要做的事情就是那就是真的去删掉这些个数的点。对，那所以为了要找到那个个数的点，我们就第一个先去看那个最小的 separating edge set。那这些边的集合就是它的大小就会是跟 H connectivity 是一样的，所以我们再从这边出发。 所以我不会说这里的 A 跟 B 是可以随便的 A 跟 B。
哦，
对，但我们也确实没有用到这个特性啊。
可能是说，假设说这里交换了，就假设这边是 A，这边 B， 你这边
也可以啊，也可以，这个可以，
都是
对你也可以说这边是 A，这边是 B，这个我觉得没有问题，
对，这边就是没差的。
对，这边没有问题，对。 Okay, so next we're going to discuss two kinetic graph. Okay. Okay, so before I give you the claim that we're going to prove, let me first give you some motivation. Okay. Okay. So before we discuss kinetic graph, let's recall the definition of kinetic graph. Okay, just kinetic, not too kinetic. Okay. So if a graph is kinetic, then by definition, for any two vertices, U and V, you can find a path. Right, this is a definition of a kinetic graph. Okay. So I can replace this with one kinetic. Okay. So if the graph is one connected, then for any two vertices U and V, there's one path between them. Okay. Now how about we increase the connectivity? So can we say that if the graph is two connected, okay? Recall that two connected means if you only remove one vertex, then the graph is still connected, okay? Or you need to remove at least two vertices to disconnect the graph. So this is stronger than just a kinetic graph, okay? So for these stronger graphs, can we have stronger guarantees? Can we have not one, but two paths, okay? So this is what we're going to show show next, okay? And actually, we can prove that there's a stronger condition or stronger result. That is, this is not just two paths. These are two internally disjoint paths. Okay. So internally disjoint means these two paths that do not have common internal vertices. Okay. So here we have two paths, right? So this yellow one, well, this is P1, and the blue one, this is P2. They are both paths between U and V, okay? So their endpoints are the same, but all their internal vertices are different, okay? They do not share internal vertices. This is internally disjoint path, okay? So actually, if the graph is two connected, then not only that you can find two paths between U and V, you can actually find two internally disjoint paths. So these internally disjoint paths are quite powerful because if you consider computer networks, and if you have two internally disjoint paths, then this means if just one switch or one machine fails, you can still use another path because the other path cannot use the same machine, okay? So it means better fault tolerance, okay? OK， 好，所以我们接下来就是要看这个 two kinetic graph 的状况，所以我们等一下要去说明说，只要这个 graph 是 two connected， 那对任两个 vertex 你都可以找到2个 path， 而且这2个 path 不会共用任何的 vertex， 除了 endpoints 之外 ，OK。endpoint 是一样，它因为都是介于 A 跟 B 介于 U 跟 B， 连接 U 跟 B， 那中间的都不会一样 ，OK。所以这是我们接下来要说的。And as a corollary, you can see that if this is a two kinetic graph, then for any 2 vertices U and V, there's a cycle. Okay, so this is one implication of the result. But anyway, let's consider this claim where we want to find 2 internally disjoint paths. Okay, so the proof is quite clever. It is based on induction. And by induction on the distance between U and V. By distance, I mean the shortest distance, where we measure distance by the number of edges. Okay. So we use induction on DUV, that is the number of edges on the shortest path between U and V. Okay. And since this is an induction proof, we need to start with the basis. So the basis is when DUV is 1. Okay. Okay. Okay, so if the shortest distance between U and V is 1, this means there's an edge between U and V. Okay, so we have to show that for this kind of graphs, there are 2 internally disjoint paths. Okay, so clearly we already have one. That is, this HUV alone is a path between U and V. So next we're going to somehow argue that there's another path. Okay. That connects U and V without using this edge. Okay. So this is our goal. Okay. OK， 所以确定一下，我们都有在同样的出发点。OK， 所以我们接下来就是要用 induction 去说明，就是数学归纳法去说明，任何2个点 U 跟 V， 你一定都可以找到2个 path， 然后这2个 path 就连接 U 跟 V， 而且这2个 path 它们中间的点都不会共通，都不会共用。OK， 然后我们刚刚说这里的 induction 就是我们会去看 U 跟 V 的距离。OK， 所以 basis 就是 U 跟 V 的距离是1的时候，换句话说 U 跟 V 也直接有一个 edge 相邻。所以接着我们就要去找，如果我们要证明就是我们最后那个2个 internally disjoint path， 我们代表它要去找另外一个 path。Okay， 那这个另外一个 path 它不能用到这个 UV 这个边。OK， 所以有人可以看出来为什么一定可以有另外一个 path 吗？当然，我们这边的假设就是它是 two kinetic graph， 所以铁定你会需要用到 two kinetic graph 这个形式。 所以有谁可以看出来为什么 U 跟 V 它一定有另外一个 path 连接，然后这个 path 不会用到 UV 这个边。Okay, so if you want to show that there's a path between U and V without this UV edge, you only need to show that after you remove UV, this edge, U and V has a path. Okay? Or even better, you can show that the graph is connected after you remove U and V, the edge between U and V. So if the graph is still connected after you remove this edge, then since by definition the graph is connected, so there's a path. Okay, so now the problem is how to show that the graph is still connected even if you remove this edge. So why? So but two connected considers vertex. Okay, so it means if you only remove one vertex, the graph is still connected. But this time we remove edge, not vertex. But you're right, we should use the property that, or the assumption that kappa G is at least 2. Right. Exactly, okay. So we've shown that the edge connectivity is an upper bound for the vertex connectivity. So if the vertex connectivity is at least 2, this implies that the edge connectivity is at least 2. In other words, if you only remove one edge, it is still connected. Okay, so that's it. Okay, so this is the proof for the induction basis, where we consider U and V are really, really close. They are actually neighbors. Okay, so in this case, one of the two internally disjoint paths, where it's just the edge. Okay, and all we have to do is to find another path. Okay. Okay, so 这个 basis 有问题吗？ Okay, so next we have the induction hypothesis, 数学归纳法的那个假设 okay? And because we apply induction on the shortest distance, so we're going to assume that the claim holds when DUV is like L minus 1, then we want to show that it also holds when DUV equals L. Okay? Okay, so I want to write out the complete claim for this case. Okay, that is that still G is a two-connected graph. Sorry, I should change. No. this can be equal. Okay. Okay. So this is our induction hypothesis. Okay. So in other words, we only consider vertices with distance L minus 1. And then we try to show that this is also true, even if we consider vertices that are L edges apart. Okay. Okay, so okay, so next we're going to consider the case where U and V have a distance of L. Okay. Okay. So in order to use the induction hypothesis, I will consider the vertex that is just before V. And this is the shortest path between U and V. So this is shortest path between U and V. Okay. And since W is the one that is just before V, this means we have exactly L minus 1 edges between U and W. Okay. And then we can apply our induction hypothesis because we have something to say about U and W because they are L minus 1 edges apart. So according to our induction hypothesis, well, since their distance is L minus 1, so we know that there are two internal disjoint paths. Between U and W. Okay. And let's call this two path P and Q. Okay. Okay. So this is U, this is W, and this is V. And we have two paths. So this is P, and the other is called Q. Okay? And recall that our goal is to find two internal disjoint paths between U and V. Okay, not between U and W. All right? So it's like somehow we need to extend these two paths. All right? But then later you're going to see that it is not actually the case. Okay, so we'll find a different trick to find these two internally disjoint paths between U and V. But anyway, we need to utilize these two paths. Okay. Okay. So first, let's consider a simple case. Okay, and see if you can figure out how to create these two paths. Okay. So the first case, which is an easier case, happens when V is P or Q. Okay. So in other words, this is U, this is W, and this is Q, and this is P, and V is part of these two paths. Okay, so this is case one. OK， 所以我们会考虑的第一个 case 就是这个 P 跟 Q， 它们经过的点事实上就会经过 V， 所以我这个图换句话说就画的不是很标准。OK， 我这个图就没有办法表示这个 case， 但是这个 case 是比较简单的，就是在这个情况下，我是假设 V 是在蓝色这条 path， 但这另外一个黄色也是一样 ，OK， 所以我们就姑且假设它是在下面蓝色这条。所以在这个情况下，我们要怎么找到两个 internally disjoint path， 然后是介于 U 跟 V 中间？不一定，所以中间这里可能是因为它有可能有很多个边。我并没有把在这个图上面，我并没有把所有的边画出来。对，换句话说，上面也是有可能会有很多个点 ，OK， 然后只是 V 是其中一个。OK， 所以在这个时候，所以我们就 focus 在右边这张图就好了。所以右边这张图，我要怎么找到两条 path， 然后这两条 path 是介于 U 跟 V， 等于说连接 U 跟 V， 然后它们不会有中间不会有共用的 vertex。所以很简单 ，OK， 所以就两条。所以第一条就是长这样子。第二条是这样子 ，OK， 所以这是一个很简单的 case， 应该可以区别出来 ，OK， 所以这个是我们叫 P2， 然后这个是 P1。怎么了？你说 ，OK， 好，所以这是 case one， OK， let's consider case two. Well, case 2 happens when V is not on P over Q, okay? Okay, so this is the tricky case. So let me check my notes. Okay, so for case 2, the idea is to find a third path that avoids W, because you can see that these two paths, they all use W, okay? So we want to find a path that, well, does not use W, okay? So that's our goal. So can we show that we can always find a path between U and V without using W? 对，因为这两个目前都有经过 W， 所以我们家的 high level 的 idea 就是要找到一个 path。那这个 path 一样是经过 U 跟 V，OK， 应该说介于 U 跟 V， 连接 U 跟 V， 但是它不会用到 W。所以第一个我们要先确定一下这种 path 存不存在。介于 U 跟 V 的 path， 但是不会经过 W， 有没有这样的 path？ 嗯哼。这样的话就等于你的 U W 就多一个，就是这样子，这样它不就是上个 case， 就是在那个其中一个 path， 就是你要243，就是243，啊哈。所以如果你在 U V 多加一条线，就直接画一条线，这样的话就代表你作为走到 W。 对。所以这样的话就是上面那个 case 就是你会滴在那个其中一条到 W path 里面，这样不是 OK， 但是这个绿色的 path 有可能会跟它有 internally disjoint， 有可能会有共用的 internal vertex， 所以刚刚这个黄色跟蓝色特别的地方是它们是没有共用的中间的点。那我这个随便画了这条绿色的，它没有这个需求，它唯一的需求就是它不能用到 W， 所以有可能画出来会长这样子。OK， 这样也是 OK 的。OK， 那所以但现在我们不用管那么多，我们现在唯一要考虑的问题就是有没有可能找不到一个 path 说它不会经过 W， 但是它可以从 U 走到 V。所以换句话说，有没有可能所有从 U 走到 V 的 path 都一定会需要经过 W？ 有没有可能？然后不要忘记，我们这个 graph 是 two connected graph， 所以有没有可能？OK， so 如果这是 two connected graph， 没错，所以我们如果把 W 删掉，那这个 graph 一样会是 connected。OK。因为只删掉一个点是 OK 的 ，two connected 你可以删掉任何一个点都还是 connected， 所以你删掉一个点，这个图还是会是 connected。既然它会是 connected， 所以 U 跟 V 就一定还会有一个 path。OK。Let's call this path R. Okay. 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 So now we have all the ingredients. Okay, we have all the components to create the two internal disjoint path between U and V. 所以你们根据上面这 这些画的，然后找到两条介于 u 跟 v 的边的 path， 然后这两条 path 没有中间都不会有共用的。可以看得出来吗？所有的边都在上面了，所有你需要的边都在上面。OK， 那所以要怎么画？一个经过 W， 所以是要黄色还是绿色？对吧？黄色还是蓝色？
在这个图的话，就是一条是绿加黄，
一条是绿加黄，
对，然后另外一条是蓝色，就点 W。
所以其中一条是蓝色，然后走到这边，然后另外一个，可是这样子他们就有共用的中间的点。
那中间就是直接切到那个绿色切到黄色，因为他们会碰到。
对。
对，所以就是先走一段绿色，接到黄色，再走一段绿色，跑到这上面那两个耳朵。
啊哈。差不多差不多。所以这边我们要看的是，就这条刚刚找出来这个 R， 最后一个在 P 跟 Q 上面的点。OK， 当然有可能它都没有了，就如果都没有的话，那就直接选这个绿色。OK， 所以确实有可能是长这样。OK， 如果长这样就很简单。OK， 你就黄色、蓝色随便挑一条，再挑一条绿色就可以了。OK， 所以这是简单的 case。比较稍微复杂一点的 case 就会是长这样子。OK， 哈？
这边就蓝色，如果这个情况，就是变成下面三个。这个情况就是蓝色是不能经过 W， 然后黄色是要经过 W。
对，所以这边的关键是我们要去看最后一个，就 R 在 R 上面最后一个在黄色或蓝色上面的点，我们叫它 Z。OK， 所以你会看到过了 Z 之后就没有在黄色，或者就没有在 P 跟 Q 上面，把 P 跟 Q 稍微。OK， 所以如果是这样的话，我们其中一条就可以长这样子。OK， 所以这其中一条，然后另外一条就是走黄色的。OK。Okay, so that's it. Okay. So I think you can transform this proof into an algorithm. Okay. So it's like dynamic programming, where you first consider closed vertex pair, okay, because we use induction on DUV, okay, on the shortest distance, okay. So you can first consider the vertex pair that is one edge separated, and then we can use this proof to find two internally disjoint paths. So one is just the edge, and the other is you first remove this edge and find an arbitrary path between them. So this is for the induction basis, or for the case where U and V are adjacent. Okay, and then you can gradually expand this distance. Okay, and for this case, we can utilize the path we have computed before for vertex pair with shorter distance. Okay, so we first, given this P and Q, no, so we first have to compute the shortest distance, find W, and find the two disjoint paths between U and W, remove W, and find another path, this path R, and use this three paths to create a two internal disjoint path. Okay, so otherwise I think that the problem is not very easy. All right, so yeah, so given two vertices, output two internal disjoint paths. Yeah, this is I don't think that's trivial, and this is the proof actually gives you an algorithm to compute two internal disjoint paths. OK， 所以我刚刚只是说，这个有机会，这个 proof 可以把它变成一个演算法。OK, so next, I'm going to just write down a few equivalent conditions for two kinetic graphs. Okay, so first one clearly because we consider two kinetic graph, so by definition, the connectivity is at least two. And the next one is also easy. Okay. If it is a two kinetic graph, then it means it is first connected, and it has no cut vertex. Okay. So in other words, if it has no cut vertex, then kappa g is greater than 1. Okay. Okay. So if kappa g is greater than 1, then kappa g is at least 2. Okay. So this there's two conditions are equivalent. The next one is the claim that we just proved. Okay, that is for any two vertices in the graph, we can find two internally disjoint paths. And the next one is a very simple implication of the third one. That is, if you have two internally disjoint paths, then you get a cycle. Right? And similarly, if you have a cycle, then you have two internally disjoint paths. Okay, so the last two are equivalent. And the final one the minimum degree is at least 1, and for every two, this time not vertices, but edges, okay? So for every two edges, there's a cycle that contains these two edges. Okay.好，所以这些都是一样的，在讲一样的东西 ，OK， 都是在讲这个 graph 是 two connected，OK，、所以前面1、2、3、4这个就是我们前面刚刚都已经讲过了。那最后一个是就是我们之前没有看到，就是如果我们今天这个 graph 是 two connected， 那就代表，你随便挑2个 edge， 你一定可以找得到有一个 cycle， 这个 cycle 它包含这2个 edge，OK，、这个是。也是跟前面的 two edge connected two connected 是一样的 ，OK， maybe I have time for one proof. So let's prove 5 implies 4, okay? That is, if you know that the minimum degree is at least 1, and for any two edges, there's a cycle containing this pair of edges, then for any two vertices in the graph, there's a cycle containing these two vertices, okay? So 5 implies 4. It's like starting from two edges, and you go to two vertices, and you want to find a cycle, okay? So OK， 所以我们接下来要证就是4是对的。那前提是，如果我们知道5是对的，那4会是对的 ，OK？ 所以如果你想要证4是对的，你就要证，所以有一个 U 在这边，有一个 V 在这边，然后它会有一个 cycle，OK？ 所以这是我们想要证 ，OK？ Okay, so the assumption is that the minimum degree is at least 1. Okay, so if the minimum degree is at least 1, this means U has a neighbor and V has a neighbor. Sorry. Mm-hmm. 对，就是如果是没错，所以呀，如果你要说的话，这边你也可以把它改成 two。对，你是对的 ，OK。但我们的 proof 不需要用到这个 two， 我们只需要用到1而已 ，OK。对 ，OK。就是不管怎么样，它都一定至少会找到一个 neighbor，OK？、所以 U 会有一个 neighbor U prime，V 也会有一个 neighbor V prime，OK？、 所以如果最后一句话这句话是对的，那就代表会有一个 cycle，OK？、这个 cycle 会经过这两个边，那基本上4就正完，因为4就是这个 cycle 就是经过 U 跟 V，OK？、所以逻辑上比较像是这样，就是对这两个 U 跟 V， 我已经先固定这两个 U 跟 V 了，那我接下来要证的是 U 跟 V 会有一个 cycle。那我一旦固定这两个 U 跟 V 之后，我就可以说，因为U 跟 V degree 至少都是2，所以它一定至少都会有个邻居，所以根据5，它就有一个 cycle， 所以有一个 cycle， 那这个 cycle 当然也会经过 U 跟 V，OK？、好，还有一点点时间，所以我们再来看一下，刚刚是5 implies 4，接下来我们来看4 implies 5。OK， 所以就4是对的，然后我们要讲到这个任两个 edge 都会有一个边这样子。OK， Okay, so this is our goal. Okay, so starting with 2 edges, and you want to create a cycle. Okay. And also we have to show that the minimum degree is at least 2. But this one is easy because for every 2 vertices, we can find 2 internal disjoint paths. So this already implies the minimum degree should be at least 2. Okay. So let's focus on the cycle part. Okay. So I want to find a cycle that passes through this 2 edges. Okay. And what we have is property 4. So property 4 tells us that for any 2 vertices, like U1 and V1, we can find a cycle. But this time, we want to make sure the cycle passes through these 2 edges. Okay. So the trick is we're going to add 2 vertices, A and B. Okay. And I claim that after you add these 2 vertices and these 4 edges, the graph is still 2 connected. Okay, so since the graph is still 2 connected, so there's a cycle that contains A and B. Okay, this is by property 4. Okay, for any 2 vertices, there's a cycle. So how to create the cycle we need for the original graph, where we just replace this V shape with this H, U1, U2, and V1, V2. Okay, so that's it. So the trick is to add these 2 helping vertices, okay, and these 4 edges. And then you can use this green cycle on the new graph to create the cycle you want for the original graph. Okay. All right, so that's it, okay? OK，那记得下礼拜我们没有上课 ，OK， 下礼拜校庆。然后在校庆的下一周，我们就要 paper 的报告。